Hello, everyone. My name is Kelly Hall. I'm a marketing coordinator for ALS North America. I want to thank you all for joining us today for our Webinar Wednesday series. Our presenter today is Dwayne Bennett. Dwayne received his Bachelor of Science in Chemistry from St. Xavier University in 2005. He is a professional chemist as a member of the ACPA, as well as the current president of the ACPS. Dwayne has been with ALS for 10 years as an expert in particle size analysis. Now he serves as the technical specialist at our ALS laboratory in Saskatoon. Today, Dwayne will be discussing particle size analysis. During this presentation, you may use your chat box, ask a question, or raise your hand features. Just as a reminder, all questions will be answered at the end of the presentation. Dwayne, thank you again for taking your time to deliver this webinar today. I will go ahead and turn it over to you.
Thank you, Kelly. Hello all. So as Kelly said, I'm going to be speaking on particle size analysis. It's more of a method overview and considerations for clients of ALS. So just to start off with the agenda, we'll start, as we start most of our presentations with a safety moment, followed by an introduction into particle size analysis, a little bit into the methodology that we use in order to present the data to clients, and then some information about the application of the results. So for the safety moment, I chose a fairly easy one, just driver safety. So if we're driving in order to go on vacation or going to see clients or even going on the road for work, it's good to make sure that we're considering driver safety. So the first one, never drive while under the influence of alcohol or drugs, which may impair your driving ability. That includes drugs that are prescribed by doctors, which may affect you. Always wear a seatbelt. Never use a handheld mobile device while driving. And if you're making a long trip, consider fatigue management, know where your stops are going to be, and plan ahead. Maybe have a second driver available. So going right into the topic with particle size analysis. Particle size of soil is a physical property that can influence a large number of other properties of the soil. If you have a lot of small particles, then you could run into issues where you are having higher upkeep because of a higher surface area, more active sites. It directly affects the hydraulic conductivity and soil vapor mobility, which means that if there's rainfall or a spill, that if it's a very coarse material, it could travel through that soil faster than if it's a fine material. It can be used as a tool to identify guidelines that need to be used for soil remediation. And it's also an important consideration for a number of different aspects of engineering, including roadway projects and construction. So when considering remediation in Canada, we have the CCME guidelines, and they have a fine coarse classification, which is based off of the 0.075 mm size, which means that we evaluate the soil to tell whether or not its median size is greater than 0.075 or less than that, which may actually change the classification and the guidelines that need to be used. So if your soil is coarse because it's greater than 50%, greater than 5 micron, then you have different guidelines that you have to meet for that soil. Also, when it comes to remediation, after the soil's been excavated, usually we have to have a fill soil, and when we're filling that soil back in, it's important to know what is in that soil and the type of the soil that's being used as the fill soil. So a lot of the situations that we use, we have to consider it in terms of the type of soil it is, as well as the nutrient requirements. And typically these are based off of the clay, silt, and sand percentages. So in both Canada and the US, we use terms such as soil triangle for this. And these are two example soil triangles, one from the USDA and one from the AAFC. So with the two soil triangles, we have different ways of approaching the same data. So in this situation for the CSSC soil triangle, we have sand and clay, while silt, because it's a property where the three different uh, particle sizes that we look at add up to 100. If both of these are at 0, then the silt will be at 100%. We can then use that data to find out what the soil classification would be. So for example, if it was 60% sand and 40% clay, we would have a sandy clay classification. With the USDA soil triangle, we run into a slightly different type of triangle where they actually classify it off of all three parameters. So it just moves around the triangle a little bit differently. So that same 60% sand and 40% clay would end up in the sandy clay here compared to here. So when we go to test particle size, it's not a simple test where we just set up a bunch of sieves and try and get all the sieves to be shook so that we can get the different breakdowns. We actually have a number of different methods that we have to apply in order to be able to give the full analysis. So the way that we actually analyze for the different particle size is broken down into three different types of methods. The first is a dry sieve method, where we take the soil, we mechanically disaggregate it if there's any clumps or any aggregates in there, and then we just use sieves to break it down with shaking to get the different size particles. Wet sieving, which is a sieve method that uses water to aid the soil passing through those sieves so that we can get the more finer sieves sizes through. And then finally sedimentation, which is used for the smallest of the particle sizes, where using sieves would not be applicable. So at this point, I'd like to start talking about the different standards that the methods use. So for many of our clients, we have used the ASTM D422, and that has been the standard since 1963, which combines sieving, both wet and dry, along with the hydrometer method. Over the years, that method has spawned a number of different classification systems, and a number of different regulators have requested it or use it in their actual manuals that they use as prescriptive methods. However, in 2017, D422 was withdrawn, and the reason for this was that the ASTM had decided to move towards a more specific methodology for each of the different portions. In other words, the ASTM D422 had too much into it and was unable to focus in on the specific methods. So the D422 was replaced with ASTM D7928 for hydrometer determinations, while the Sieve Analysis was moved to ASTM D6913. And what this did was allowed for more prescriptive elements of the methods to be documented in a much easier way, so that the Sieve Analysis, we could focus in on the Sieve Analysis in the one method, while for the hydrometer method, we could focus more on the hydrometer in the D7928. It gives a lot more information and it gives a much nicer breakdown of the materials. So going into the actual way that we do particle size analysis, there are a number of steps that get done in order to be able to provide the details. So we typically have to start with the samples and look at sample preparation, because as samples come into the lab, they sometimes need to be handled in specific ways in order to make the actual analysis work best. So with sample preparation, we have to first decide how we're going to handle the sample. And that's usually a visual confirmation of the sample type and deciding how it needs to be handled in order to prevent any type of physiochemical or mechanical damages to the sample that could affect the results. So typically it can be analyzed on an unmodified as received sample, or it can be analyzed on a dried and desegregated sample. And the differences between those really depend on the sample type and how the actual sample is going to react to any type of desegregation. If there's any issues with the sample, such as if it is very hard materials that could potentially break if it's being mechanically desegregated, then mechanical desegregation should not be used because of the damages to those particles. The issue with drying samples is that it can cause physiochemical changes to occur. And this can occur with heavy clays or with any type of sample where you have a lot of aggregates into it. I use example of heavy clays because most people have dealt with pottery, where you take clay, you shape it into a form that you want to hold that form, then you dry it at high temperature in a kiln, and it comes out and it's hard, brittle material. It's still clay, but it's in a different form that wouldn't pass through a clay sieve at that point. So with desegregation, typically we use a mortar with a rubber tip pestle to do the desegregation, and it's just a very, very soft way of breaking up the samples in order to prevent us from damaging any of those larger particles. The next step would be to evaluate the sample to find out what the actual specimen size requirement is. So the big thing about particle size is that the larger your maximum particle size is, the more sample you need to use in order to get a representative analysis at each of the different levels. So if you have a large number of large particles, such as a 3-inch or 76 millimeter size particles, you require a very large amount of samples ranging on 70 kgs in order to be able to get representative samples on each of the sieve levels. Otherwise, when you get down to certain sieve levels, you would not be able to get enough material in order to give a result. And the way that we evaluate the different sample weights are based off of the ASTM methods. And there are two different method types, method A and method B. Method A is a composite sieve, and method B is a single set sieve, which I'll be getting to when we get to dry sieving. So next up would be dry sieving. So then we get a little bit of information on sieve analysis. So as I said before, there are two different types of sieving analysis. The first being dry sieving, where we can approach samples in two different ways. The first way is a composite sieving, where the material is broken into two separate portions. A coarse portion, which is greater than 2 millimeter, and a fine portion that's less than 2 millimeter. And each subset is then sieved in order to get their different portion sizes and then mathematically combined. The second way is a single set sieving, where we take the entire sample and we put them into a sieve rack and allow us to analyze the entire size range. So this is just an example of a sieve stack where we have a number of different particles ranging from coarse to fine particles. Each sieve has openings in it that allow particles that are smaller than the openings to travel through it and go down to the smaller sieve. By putting a rack of 4 sieves onto a shaker, the particles will slowly make their way down to the size through the sieves till they land on a sieve where they can actually be retained. The big thing about sieve analysis is that aggregates, such as clay aggregates, may stick onto one of the sieve sizes where we want to actually pass through, because this actual clay aggregates can be broken down to smaller particles. That requires other methods such as wet sieving in order to break it down. So in order to move on to the wet sieving and sedimentation analysis, we do have to do some pre-treatment of the samples. So the first type of pre-treatment is based on the types of samples that we're dealing with. If samples have high organic matter, then we could have issues with the settling rates for sedimentation, where the organic matter will basically float and will not actually settle at the proper speed. And the way that we remove organic matter from the samples is through a digest using hydrogen peroxide. Carbonates are a known issue for particle size analysis, as they can actually cause clay particles to stick together as cementing agents. And we remove the carbonates through acid treatment. And the salinity of the soils, if there's a lot of salt content in the soils, may affect the density of the dispersion fluid. It will dissolve into the dispersion fluid and cause issues, which will affect the sedimentation methods. And the way we do, if we deal with saline soils, is by treating them with washes to remove the salts. Following any type of pretreatment to remove interferences, we do have to do a dispersion. So typically samples are dispersed in using one of two different methods for chemical dispersion. The first is just using water. So you take the soil sample, you disperse it into water with shaking or mixing, and then it'll be dispersed. For a lot of samples, and as our referee method, we do use Calgon solution or sodium hexametaphosphate as our dispersing agent. And what sodium hexametaphosphate does is it acts as a separating agent where it will attach itself to individual particles and force the particles to disperse by basically making them charged. So the individual clay particles will not stick together, they'll actually fully disperse as the sodium hexametaphosphate gets between them. For mechanical dispersion, we do use a number of different tools in order to help disperse the samples. The first is a milkshake mixer, which we have a nice picture of here. The way a milkshake mixer works is it adds air into the samples and those bubbles help disperse the soil particles. And they do this by using baffles. Air jet device has a number of different openings down at the bottom of a cup, which allows air to be forcibly put through the sample, which those bubbles help disperse. And the use of a mechanical shaker allows us to put the sample onto a shaker, and just that rocking motion of that shaker will cause the soil particles to just disperse in a gentle motion over time. The advantage of the milkshake mixer is that it's fairly easy to use. It doesn't take long to actually mix using a milkshake mixer, and it's fairly easy to clean the cups. Airjet devices require intense cleaning between uses because the cups have a number of different air holes in the bottom of them, as well as to clean the different surfaces within them, but are advantageous because you don't have a mechanical mixer, such as a mechanical mixer, which would potentially break up larger particles or that could be frail. The mechanical shaker is a very versatile method for doing a dispersion. However, the disadvantage of a mechanical shaker is that it takes a significant amount of time to disperse it because it is not an aggressive dispersion method. So moving along to sieving and to sedimentation methods. For wet sieving, what we do is we use a sieve, usually a very, very fine sieve, to sieve the samples, and then we use DI water to wash the sieve and wash the material through the sieve. Then we collect the material that's retained on the sieve and weigh it. It's very important to use wet sieving when doing the more finer mesh sieving, simply because of the fact that a lot of the material likes to stick to the sieves or block the sieves, and aggregates can easily form and block the sieves. It also helps break down clays and colloidal materials which may stick to larger particles, and that can influence the results. Moving along to sedimentation methods. So sedimentation refers to the settling rate of the particles in the dispersion. So the big thing about sedimentation is a very useful tool for doing the very small particle sizes, such as your silts, your clays, and your colloidal materials. So the way that it works is based off of Stokes' law. So over here, I do have a image of a graduated cylinder with a number of different particles into it. And the principles of Stokes' law is that the particles that are bigger will settle faster than the smaller particles. So as the time passes, those particles will slowly start falling out of solution. And then if we take a reading, we'll get a reading of the material that's still in the solution or still suspended. Then we wait, we get more particles falling out, we take another reading, and that's only going to be the smaller particles. With Stokes' law, there are a number of assumptions that are made. The first being that all the particles in the soil are spherical particles. They all have smooth surfaces, and there are no inter-particle interactions. So by combining the settling principles and the measurement, we can determine any reading at time t. So by taking certain readings at specific times, we then can chart those in a grain size curve, and using either a hydrometer or a pipette method, we can determine the amount of particles that are still in suspension. And by using Stokes' law, we can also determine what the largest particle size is in the suspension at that time. So the first method that we're going to be looking at is a hydrometer method. So a hydrometer method for sedimentation, it is the referee method. And the way it works is that it's based off the relative density of the suspension. So as the hydrometer is put into the graduated cylinder or the sedimentation cylinder, based on the density of the material, the hydrometer will either go further down or will float higher up. And by the actual height of the hydrometer, we can measure the density of the solution. Based on the time, the temperature, and the reading, we can then determine how much material is still in suspension, as well as the particle size of that material. So we'll take readings intermittently for up to 24 hours. For certain materials, we do have to go up to 48 materials for the colloidal materials. So just to give an example of some hydrometer determinations, these are 4 hydrometers that were put into graduated cylinders. And we can see that the first one is much denser than the other ones, as the hydrometer is sticking much further up out of it. So that would tell us that the material is still in suspension compared to the other 3 where most of the material has come out of the suspension. The second method of doing sedimentation would be the pipette method. And the way that the pipette method works is it's a direct measurement of the material in suspension. The subsample is taken of the suspension in the same way that the hydrometer readings are done, except where we actually take a subsample. And it has to be taken at specific times and depths. If you vary the depth, you're adding in extra uncertainty to the results. That subsample is then dried and weighed, and that gives us a direct measurement of the actual material itself. And the big advantage of the pipette method is that it can be miniaturized, where the hydrometer method, you have to maintain specific sizes of the sedimentation cylinder as well as the hydrometer. The pipette method, you can miniaturize it to a certain extent based off of your minimum sample size as well as the use of the balances for taking the measurements. So to compare the 2 methods, the hydrometer and pipette methods are both very comparable. This is a overlap of the 2 different types of methods, our pipette method as well as a hydrometer method, which give very comparable results. The big differences between the 2 is the efficiency and the actual analysis requirements. So to do a hydrometer method, it's a lot easier and it's an immediate read. While with the pipette method, it requires a certain level of knowledge about the method as well as experience with the method in order to ensure that you're taking your pipette readings at the correct times, the correct depth, and it's a technique issue. The other issue is that it does require significant drying time in order to remove the moisture and get those readings. Typically, the choice between a hydrometer method and a pipette method is regulatory standard dependent, wherein hydrometer methods are typically a referee method. So moving on to the reporting of particle size. So there are a number of different ways of reporting particle size. Typically, they're broken down into two different ways. One is a report based off of the percent passing. So at that time, we would choose a number of particle sizes that are important to the client and report how much of the material is passing those specific particle size thresholds. And that can easily be graphed onto a curve called a grain size curve, which we also can issue to the clients as needed. The other option is to classify based on defined particle size ranges. The issue with defined particle size ranges is that you have to establish which particle size ranges you're applying to, which it depends on the regulation. So there are a number of classification systems that exist, and each are focused on specific applications. The Wentworth system is a well-known system. It was established in 1922 and is still used. Then we have the AASHTO, which is for the highways and different transportation. There's the international standard, the unified standard, the USDA standard, as well as the CSSE standard. So just to give a little bit of a breakdown of the actual particle sizes that are used, there is this graph that is shows the different particle sizes. And we can see that for many different systems, they use for clay 0.002 mm for USDA and the international standard. However, for AASHTO, they use 0.005, and that is also the standard used in Canada. For Wentworth, they break it down a little bit further as well, and they have different fractionations of sand built into that as well. So knowing the classification system that your regulations require is important for the reporting of this. Again, coming back to the different types of reporting in both USDA and CSSC, we do have the soil triangles again. Both are very important for evaluating specific soil sizes or evaluating nutrient levels if we're looking at agricultural evaluations. In certain situations, based off of the soil classification, it can change the way to evaluate the results. In the situation in Canada, we have specific densities that we assign to soil classes, which can change depending on how fine or how coarse the material is, or where it falls on the soil triangle. For grain size, or for more complex particle size, we do offer graphing of the particle sizes. So this is a percent passing versus the millimeter of the grain size. And the way this works is that it's a typical S curve. So as the particle size decreases, less particles are going to move through the actual sieves, or through the dispersion, we can establish that the particles are less than a specific size. So as we go left to right, we will see that more particles are being captured through sieving or through the dispersion. So we start having less particles passing through those sieve sizes until we reach the bottom where we are down into the clay dispersion ranges. And the way that we can use this, or clients can use this, is to compare it to allowed regulatory limits, or to just extract out any particle sizes between the points. So the next step is, how do you actually pick a particle size determination? So the way that we would be looking at choosing a particle size analysis, what type of analysis you need, is really dependent on the application and the regulator. So a lot of situations, the sieve analysis are standardized, even if it isn't subscribing directly to one of the ASTM methods. The methods are very similar to those ASTM methods for sieve methods. The choice between sedimentation methods can be prescriptive. I know when we look at the CCME guidance documents, they do specify to use hydrometer methods. And we need to know what you're looking for. So if you're looking for specific AASHTO, we need to know that so we can report the parameters that are required for the AASHTO classification. There are other specific methods that need to be used, such as if it's CCME fine coarse. If it's ABT1, Alberta Tier 1 fine coarse, it's slightly different, as well as if there's a grain size curve, which classification system we're going to be using. So the simplest application is the CCME fine coarse classification, which is based off of 0.75 mm. And if the materials are fine, according to this classification system, we do have higher surface area. It will actually hang up organic materials or organic contaminants a lot better than coarse materials, which have low surface areas. So in that situation, if we apply CCME guidance to that, we can actually see on the bottom here for hydrocarbons in the diesel and motor oil range, coarse grain materials have a lot lower actual ranges for regulatory guidelines compared to fine grain. And that's simply because the fine grain materials will hold up those materials a lot better than the coarse grain. This coarse grain material, it could get into your water supply, it could spread a lot faster. With Alberta Tier 1 guidance, they include a concept referred to as very coarse materials, which has greater than 70% of the material, which is greater than 2 mm. And when we have material that is in that range of very coarse, it means that there's going to be a lot of mobility through that material, so it requires a different approach compared to a Tier 1 approach. Coming back to the soil classification systems, the CSSC classification systems, when we're applying it to soil nutrient levels or the evaluation of fertilizer recommendations, we do have a way of applying the soil texture class, sand, loamy sand, clay, silty clay, etc., to the nutrients based off of the actual density of the material, which can affect the results greatly. If you go from a coarse material like sand, which has a density rating of 2.2 compared to a clay, which is 1.7, it could affect the actual amount that you need to apply to actually get the fertilizer levels high enough. Another application actually comes from ASTM C33 specifications, and what ASTM C33 is its concrete applications. And concrete applications apply to the mixing of concrete, but also can be applied to septic field specifications. And this is an example that we get a lot of work for in Canada, where the material must fall into a specific size class in order for it to be suitable for a septic field. If it's too coarse, the material may not be retaining the effluent, which means that it could be spreading over a much wider area, could potentially get into water tables or water sources that we don't want it to. While if the material is too fine, it may clog up and may no longer be useful as a septic field. So the application of this is to use grain size analysis, which we can use here. So I have the green areas of this grain size curve marked off as kind of the Goldilocks zone for septic field soil. And if the soil falls into that area, it will be suitable. So in this situation, we can see that the particle size line in blue does fall outside that line for a number of different particle sizes. So this material might not be suitable for actual septic field. If it falls over on the left side of the green line, the material could be too coarse, so it won't hold up the material enough. While it falls on the right side of the line, it's too fine, so it may clog up too fast. The application for particle size analysis for roadways is also very important, as if the particle size is not correct for a road and you do not consider it when you're putting down the road, it can actually cause major issues such as washouts or damages. This is an example of a roadway where the road actually washed out and a lot of damages and a lot of repair work, multi-year project to repair the roads. The AASHTO regulations require specific particle size, or if the particle size of the roadway is not suitable, you need to consider it in different ways. So, for example, this is the classification of the different aggregates for roadways. So if it's in the excellent to good ranges here, which are these ranges here, you have so much passing your 0.425 mm range needs to be 50% max. Your 75 micron needs 25% max. Then it is considered an excellent to good material compared to other materials, which could be lower classes down here, which are your silt and clay materials that could easily be damaged or washed out. When it comes to concrete evaluations, we use the same type of classification system. If the material is too coarse, it will not hold together as much and it won't have enough room for the actual concrete material to take hold. While if it's too fine, it does not make up a good material either, because it will become crumbly concrete and will not hold together. So to move on to different providers within ALS, we do have a number of labs that offer the different types of determinations. The first is the PSA 1 applications, as well as PSA must or PSA CCME for the fine coarse classification. And most of our labs in the Prairie region do offer this type of determination, including Calgary, Edmonton, Saskatoon, and Winnipeg. For grain size determination, which is the more complex applications such as the Wentworth or the AASHTO, Saskatoon, Waterloo, and Winnipeg all offer those types of determinations. In the United States, we do have grain size determinations following ASTM D422, which is similar to ASTM D6913 and ASTM D7928. Just we haven't moved over to those standards because they're not requested often. Both our Tucson and Kelso labs offer those. So moving on, just these are the references referenced here. There is the ASTM 422, which has been withdrawn, as well as a couple of the other manuals and methods that we use. And just for contact information, I'm based out of our Saskatoon lab, which is in the middle of the Prairie region in Canada, and I'll open the floor for questions and for Kelly.
Yes, thank you, Dwayne. We will go ahead and open it for questions. Again, you can use your chat box or the ask a question box, or even the raise the hand feature if you want to ask Dwayne a question directly. We'll go ahead and give everyone a few moments to write those questions down. I do want to let everyone know that we do record our webinar presentations. All participants of this webinar do receive a follow-up email once the recording is available to view. We also post our webinars on our ALS Global website and our YouTube channel. I also want to let everyone know that due to the reception of this topic, Dwayne will be presenting this webinar again on October 2nd. So if you have any friends or colleagues who were not able to join this webinar today, Dwayne will be presenting again on October 2nd. You can subscribe to our Webinar Wednesday emails on our website to receive invitations to these upcoming webinars. I do have a few questions coming in, but they are all about getting a copy of this presentation. So I just want to remind everyone that we do record these webinars and they will be posted on our website next week. Everyone that was on this presentation today will receive an email once that is available to view. I don't see any additional questions coming in, Dwayne, so I wanted again to thank everyone for attending and for Dwayne for presenting today, and I hope everyone enjoys the rest of their week. Thank you very much.